So, yeah, welcome everyone to my talk about affine group schemes. So, a little introduction about me. So, I'm a master's student at ETH. I did this topic as my bachelor thesis back in, my God, I don't even know the year. I think it was 2021. Is exactly 2021, and I did it together with Professor Peter Jossen. It is a topic which is pretty central for modern algebraic geometry. Let me quickly write the title. Schemes and the idea basically is to give a more algebraic intuition to many groups that we have already seen. So, for example, I assume most of you all are undergraduate students, which is completely fine. I will try not to use as much terminology, but I'm still trying to give like sort of an insight of what we're trying to do here. So I think a good introduction to this topic, especially the first part, which I believe is the most interesting part, the affine group schemes, has a very good motivation for people who are familiar with general linear groups. Yes. So, okay. The way I want to do it is that I will mostly use the blackboard, because I think it's more interesting if I can actually like work on something instead of just showing on a projector. And I'm just using the projector to just show some definitions instead of writing them, so you can always see them, etc. So, okay, the idea of an affine group scheme is the following. So if we start with any group, like think of your favorite group. The example that I've chosen is consider the group. Let me use a different color. Oops. Consider this group. Just the group GL2R. What is this group? This group is basically just the invertible matrices with coefficients in R, which have determinant unequal to 0. Okay, so far so good. And the question here naturally is, oh, it doesn't seem. Oh no. The natural question here is, what additional structure does this group have? So it's a group. The group composition is just the multiplication, and the identity element is just the identity matrix. And the question is, what additional structure does it have? So, I assume some people of you are familiar with a topology is, or a differential manifold. And for example, in this case, we have that GL2 of R. Since R is a Euclidean space, we have a natural topology on it. So it's basically, it is even a topological space, for example. It's a topological space or a subspace of, we can say of 4, because we can naturally embed 2 times 2 matrices in R4. But actually, it's also a so-called Lie group, because it has the structure of a differential manifold. So far, so good. The issue I want to tackle here is what happens if we are not working with R? Let's say, what if we have GLN2 of Z, or GLN2 of Q, or any finite field? What additional structure do we have then? So the next question is, what about GL2 of R for any ring R? Can we say anything about the additional structure that this group has? A priori, the answer is no, just because we don't know what the ring R exactly is. And this is an issue. And the solution that affine group schemes have is, instead of looking at the entire group of this with any ring R, we just look at this as a functor. So we know that this does not have any additional structure itself, but we can kind of impose additional structure by just considering the entire thing as a functor. For those people who are not familiar with category theory, that's what I'm using the presentation for, so I can talk a bit about the terminology. So the solution that we have here is, here GL2 actually is has some more structure than just a group. It is a functor, a so-called functor. And precisely, it's a functor which goes from the category of rings to the category of groups. This is our functor. And a functor basically is some people can say it's kind of like a function, because basically what it takes as an input is anything in this category, which is just the category of all rings. And then our output is a group. When we're looking at what I've shown here, for example, here for just a quick introduction about category theory of what's actually happening here. Formally, a category like the category of rings or the category of groups is just a formal class of objects, which I denoted with C. And to the objects, we also have homomorphisms assigned. So, for example, in the category of rings, we have the ring homomorphisms. Or in the category of groups, we have group homomorphisms. We have all various examples, like category of sets, where it's just the normal maps between sets, and we also have the category of topological spaces, etc., etc. So this is this example that I have here. Usually, I use this notation for categories. Sometimes people use abbreviations like vect for vector fields, vector spaces over a given field K, or vect F for finite dimensional vector spaces, which we will see in a second as well. But this is a category. The formal details are not so important for what I'm trying to talk about today, but I still wanted to show it here so that one has an idea of what's happening. So, what we also have, what I've written here, is a so-called functor. A functor basically is an assignment of elements that I have here rings, and then groups. So far, so good. And technically, a functor also assigns homomorphisms. So what actually happens is that I also have to say where the morphisms come. So for example, if I have a ring homomorphism here from R to S, I also have to say where this homomorphism is going to. Technically, this would be a homomorphism which goes from GL2R to GL2S. And what basically happens is if I have a matrix here, I just send it to the matrix with the image components. But this is more of a detail and not something I want to focus on in this talk because it is not so relevant. Yeah, but anyway, the interesting fact here with this functor is that it has a very special property. And the very special property that it satisfies is that this functor is representable. This is our first, let's say this is our first proposition. the functor GL2 is so-called representable. Representable is a term that will appear a lot in category theory, and what it basically means is that we call a functor representable if I find an element of my domain such that I have a natural homomorphism, natural isomorphism between the homomorphism set and the image that I have here. It's kind of a mouthful to take in the beginning. It's kind of a weird definition, and sometimes one has to think about it, what it actually means. But it turns out to be a super, super convenient tool in category theory or here in the theory of affine group schemes, because it gives us the power to look at the entire functor that we have here and just reduce the entire structure that we've given here to a single element of this category, which is just the rings. In this case, we can give a representation quite easily and very explicit. I will just leave the definition here. In this case, we can just give an explicit representation, which in this case is the following ring. We define A to be this polynomial ring. It's C11, C12, C21, C22. I just need 4 variables, 1 for each component of my matrix. And then I also need another element, which I call Y inverse, where Y inverse is just technically the determinant, or not just a Y, it's technically just the determinant given by those 2 elements. And what I'm claiming now is that I can explicitly give an isomorphism the following way. I go from A to R. Let's say then for any R ring, we have an isomorphism from here to GL2 R, which on one hand I can give explicitly in this direction. I actually can give the isomorphism explicitly in both directions, but it's enough to show it in one direction. In this case, we would just send it to this matrix, phi 1, 1, phi of x12, phi of x21, and phi of x22. And what I claim is that this is actually a bijection, and a representation also requires that this bijection is natural. There's some technical detail. Naturality just means that if I change this ring here by some ring homomorphism, I just want some diagram to commute. It is just a constraint about my about my bijection here, so I cannot just write anything. It has to be natural in some kind of sense. But this is just the rough idea. So, okay, what did we do here? Actually, this is an example of an affine group scheme. Let me just quickly unmute this. Yes. What we actually done here is we've constructed an affine group scheme. Essentially, an affine group scheme is just a representable functor from the rings to the groups. So I will just quickly hold that. Oops. So our key definition here is an affine group scheme is a representable functor functor G, which may go from the rings, but we can actually do a bit more. We can say that an affine group scheme is a functor which goes from the category of K-algebras to the category of groups. K-algebras are just K-vector spaces which also have a ring structure, and the ring structure is just compatible with the K-vector space structure. One way of saying it is that here a ring, this is just a ring, or we can say this is a K-vector space with a ring homomorphism K to K to R. This also works. This is a K-algebra. Yes. But in our case, we like to reduce ourselves where we have a base field, so-called our base field. Since we still want to do algebraic geometry, in algebraic geometry, we always want to work on a certain base field, which is also going to be important when we're talking about the main theorem that I have proven in my thesis. Yes. Okay, this is the idea of affine group schemes. And as I've told before, is that I have this natural bijection. When I have a representation, A, I have this natural bijection. We call a representing object R A the coordinate ring. The coordinate ring of G, and we have a natural bijection here, which we want to use a lot. In our case, this is our ring, and we kind of have some structure that we can recover from A when we're just looking at the functor. So I have here I have my ring, and I see that I have those four components, and somehow the condition that a matrix here has to be invertible is kind of encoded into the fact that this element here, which is basically just the determinant, has to be invertible in this ring. So the natural question here is, can we recover the group structure of G alone from A? So if I have my ring A, can I reconstruct how my group G looked like? The short answer is no, but only up to a certain way. So we can say the answer is yes. The reason is with my representation, this representation that I have here, this bijection that I've written here, this is only a bijection of sets. The problem here is that the homomorphism of rings is not a vector space. I cannot add ring homomorphisms and expect that it's still a ring homomorphism. The problem is that a unit has to be sent to the unit. So this is not a group. And this is the main problem that I have here. So I don't know how the ring structure, the group structure here looks like. I only know how the set looks like because of the bijection and not the ring structure. So what do we do? The idea is I want to impose some more structure onto my ring A so I can still recover my ring, my group G. Yes? Exactly. And this is where I want to go, here. Our solution here is, we give more structure. Sure, to A. And the key word here is a so-called Hopf algebra, which is a very interesting tool, which I assume you have not heard so far because it's a very technical tool in algebraic geometry, which is based on the idea of algebras, but I just reversed the errors. So let me quickly turn on the beamer again. So the idea is the following. I start with a ring, an algebra A over a base field K. And the question I'm asking is, what is this algebra essentially? So an algebra is just a set, basically, that has a K vector space structure, which I denoted with A, which is my addition, S, which is my scalar multiplication, and then M, which is my multiplication, so that A and S give a structure of a K vector space, and A and M give a structure of a ring. And I just want them to be compatible in some sense, as they satisfy associativity, distributivity, etc. The thing I want to say here is that basically, Kelly, an algebra A is a K vector space A together with K linear maps. Now it's the interesting part. Instead of writing the maps like this, I write the maps this way. I write the multiplication as a map which goes from A tensor Ka to A, and E, which goes from K to A. And here I still have that this is just a normal multiplication, but instead of the advantage of writing tensor here, has that I can say that this map has to be linear instead of just bilinear. For people who are familiar with tensor products have the universal property that they linearize bilinear maps. And the multiplication here is an example of a bilinear map, just because of this distributivity property. So I have this. And I also have some other conditions, like I require associativity, compatibility with the unit element, etc. But instead of writing this as a formula, I can also write this as a commutative diagram. A commutative diagram is just a diagram with arrows where it requires that the composition of all arrows give the same, no matter on which path I'm going. So in this case, associativity is just the requirement that this diagram is commutative. Identity, I can turn this off. Here, I say identity, which goes from A tensor A, or I say I multiply the right side. So I have identity tensor M, which goes from A tensor A, and then I multiply on both sides. Little task for you, verify that this actually represents the associativity axiom. If you just write it down, it becomes clear, because here I multiply on the left side first, and here on the right side, which is just the same as saying that A, B, C is the same as when I do it first on the left side. It's just this, what I'm saying. I can do the same with the unit element. What happens with the unit element? I just want that the multiplication with a unit element is just the identity. So I can write it this way. I have A tensor K, and now I want to multiply these two elements, but I only have the multiplication on A. So what I'm doing is that I tensor A with K. So I get A tensor A. And here I can multiply, which gives me an element here. And I can do it on the other side. Or I can just leave it as that. I have this property, but these two tensor products, since this is a tensor product over K, these have to be isomorphic. The isomorphism can be given explicitly by just the multiplication of this element with an element here. So these have to be isomorphic, and the fact that this diagram has to be commutative is just the requirement that A to the identity times the identity element in K has to be equal to K again. We can do the same on the other side, which doesn't matter if we assume A to be a commutative ring, which we always do in algebraic geometry. But just to be sure, we could also write it this way, just so that we have a left unit and a right unit. So this would just be a right unit. And this would be a left unit. Yes? So far so good, and so far it's a bit boring. What is the interesting thing we can do here? What about we are a bit silly and start changing all the arrows? So here. So instead of a multiplication that we have in our algebra, we say we want another map which goes from A to A tensor A. And instead of a unit, I have a map which I conveniently call in Greek letters an epsilon, which goes from A to K. And this is the first motivation of a so-called co-algebra instead of an algebra. Yes, a co-algebra is basically a K-vector space, as in the algebraic sense. But instead of a multiplication, I have a co-multiplication, which is a linear map in this direction, and I have a co-unit, which is also the arrows reversed. And I also want that certain diagrams are commutative, and they are exactly the diagrams that I have written here, but I reverse all the arrows. So what I'm getting is that I require these diagrams to be commutative. And the first diagram is called the co-associativity axiom, and the second one is the co-unit. And now it's clear why I wanted to write these as a commutative diagram and not as a formula, because now it's not so easy to write this down as a formula just because of the tensor product. Not every element in the tensor product is a pure tensor, so I have to write everything as linear combinations, and it's kind of convoluted and not very convenient to write down. It's a lot easier to see it as a commutative diagram, as I've done here, and then it's clear. I just want that these diagrams are commutative, period. And this is a co-algebra. We'll see how this is useful, but just for convenience, I will do 1-2 little examples for them. So we've seen that this is a co-algebra. And right, this is an algebra. And this is a co-algebra. And it's naturally to ask if we have any examples of that. And of course we do. Prime examples are, for example, the ring over some, the polynomial ring over some indeterminate t. I claim that this can be turned into a co-algebra simply by setting that the co-multiplication sends t to 1 tensor t plus t tensor 1, and my co-unit sends t to 0. The reason why I only have to write t, or I only have to declare where t is going, is because t generates A as a K-algebra. So this map is already fully defined. And furthermore, I want this to be... no, this is fine. But another example that I have, which is also very interesting, is what if we look at the ring of all rational functions. This basically is just a ring with indeterminate t, but I also allow that I can invert t. You can say it's the ring localized at t. That also works. And I claim that I can turn this into a co-algebra by setting the co-multiplication to be t tensor t, and the co-unit is 1. This is a co-algebra. Okay, why is this interesting? The interesting fact here is the following theorem. The theorem says that if we have an affine group scheme, we can turn our coordinate ring into a Hopf algebra, which is just a co-algebra with some extra structure, which I will show in a second, so that these two categories are equivalent. So I can go from an affine group scheme to the coordinate ring and the other way around. So the theorem is the following. We have an equivalence of categories which goes from the affine group schemes over a given K. I also have to look at the opposite category, but that's not so important. It's just because I have to swap errors. But it's just a detail to the so-called Hopf algebras. Okay. Now we'll quickly show what Hopf algebra is. Have to unmute here. So a Hopf algebra is basically an algebra, which is fine in our sense, because when we start with an affine group scheme, here, start with an affine group scheme, and we have our with coordinate ring A, and we have our natural bijection. R. We already know that A is an algebra. What I'm saying now is that I can naturally give A structure of a co-algebra as well. So I have an algebra and a co-algebra structure, such that I also have some map that is called an antipode, which corresponds to the fact that I can invert group elements, so that this map here becomes a group, and this bijection here becomes a group isomorphism. The group structure I have given here with a Hopf algebra is the following. The group structure I can give here is just given by the following law. If I have ring homomorphisms from A to R, I can define A G times F as the following composition. Since A is a Hopf algebra, I can use the co-multiplication to go from A to A tensor A. But now I can tensor F and G here to go to R tensor R, and then from R tensor R to R. And this way, I'm able to define a group structure here, which turns everything into a Hopf algebra. This to a group. What technically happens here what technically happens here is that I have an explicit functor which goes from the Hopf algebras K to the category of affine group schemes, or here, op affine group schemes over K, where I send a Hopf algebra to this functor. And this is then is an affine group scheme, and I just claim that this is a equivalence of categories. Yes? Okay, what about some examples of affine group schemes? So the examples that I have are pretty simple. For example, GM, which is called the multiplicative group. GM, called the multiplicative group, which goes from the algebras to the groups. And I just say that I send R to the unit. This is a group. I can also say where the group homomorphisms go. Homomorphisms go. If I have a ring homomorphism, I can just restrict it to the group of units. And I claim that this is represented by this Hopf algebra. The same one I've written before. This one is a group. And this one is a representing object. Another interesting example is for people that may be familiar with algebraic geometry, some basic course, is I can turn the affine line or the affine space into an affine group scheme by just sending an algebra R to R to the n, and the group is just given by addition. And I say that the Hopf algebra, which is representing it, is just the normal coordinate ring of the affine line. Yes, this has a name, or this is, for example, this is the multiplicative group, and this is the affine n space. Those are some examples. Yes, but what do we want to do with that now? The interesting theorem that I have proven in my thesis is the following. Oops. Is the following. It says that any specific category that has some notion of tensor product and duals is naturally isomorphic to the category of representations of an affine group scheme. That's something I want to quickly talk about. So I also have the notion of a so-called Tannakian category. A Tannakian category is a category that has some notion of tensor product and duals. For example, I want to introduce that as an example where we have the notion of where we're working over the category of the representations of some group. So let's say if G is a group, and I'm asking myself if I have some representations. Representations are just group homomorphisms from G to GLV for some vector space V. So those are representations. And I claim that I have some notion of tensor product. For example, I can look at the tensor product representation here, which is just a group homomorphism to give GLV tensor V, which I say that I send a group element, G, to this automorphism, rho G V tensor tau G W. And I say that I have some sort of tensor product. I also have some notion of dual. I can look at the so-called dual representation, which goes from GL to GL dual, which sends AG to this automorphism. I take a linear form L, and I send it to L rho G minus 1. I need here V as well. V gets sent to L rho G minus 1. V, yes. This is my map. So, sorry for going a bit fast here. This is just the first example of a so-called Tannakian category, and we'll just quickly give its definition. So, starting here, when building a Tannakian category, I have to go in several steps. For example, I'm starting with a so-called tensor category, which, for example, here we have the category of representations of a group, G. So I have here my example, a category T together with some notion of tensor product. So I have two elements of my category, and I get a tensor product, and I just want that they satisfy some associativity axiom, which is a perfectly fine assumption. And then I also want some kind of unit object. So I want an object 1, which has the property, if I do one tensor some element, I also have the property, I can write it here actually, I have the property that I have one tensor my element x should be natural isomorphic to x. I want something like this. This is just a technical definition, which is working with an isomorphism which is not of this kind, but an isomorphism which is of this kind. This is just more convenient because then I only have one isomorphism instead of several ones for every object. But you can prove afterwards that if you have this, you get this isomorphism as well. But that's more technical. Exactly. And now we can start with a Tannakian category. So a Tannakian category is just now we have like kind of a difficult definition because I want that a neutral Tannakian category is a rigid commutative k-linear abelian monodial category. So we have to unwrap what everything means. So rigid, first of all, I need monodial. The name comes from a monoid, if anyone is familiar what a monoid is. A monoid is just a group with the property that I don't require group elements to be invertible. So a monoid is basically what I'm writing here with the tensor product is a monoidal structure because I can multiply these two, but I don't require that that elements here are invertible in any kind. So this is just my tensor product, and I have my unit object. We have commutative. Commutative just means that I have some notion of commutativity. Also a fair assumption that I have, for example, given me for vector spaces. And I also want it to be k-linear, because I want to work over a base field. K-linear just means that the homomorphisms here are k-vector spaces. I also want this. Which is fine, for example, in the category of all vector spaces over K, we know that the homomorphisms of K-linear maps are, give me 2 minutes, are again a vector space. But also, for the category of representations, this is also the case. And the next thing we have abelian. Abelian is just a certain assumption that I can do things like direct products and such. But the interesting fact is rigid. Rigid just means that we have some notion of dual. Like, for example, in the category of vector spaces, in vect, we know that the dual is defined as the homomorphisms from V to K. And rigid just means that I have duals. And a neutral Tannakian category also has some extra assumptions, for example, that the endomorphisms of the unit are trivial, and also I have that the composition or tensoring is also bilinear, and I also have that the structure is all compatible with each other. So the main theorem that I've proven in my thesis is the following, and then I'm done, is that any Tannakian category T, which has some fiber functor, which is most of the time just a forgetful functor, into the category of vector spaces, is naturally isomorphic to the category of finite dimensional representations of an affine group scheme of an isomorphic for an affine group scheme G. And that is very interesting, because I can start with an entire category, and what I'm ending up with is just one affine group scheme. And this is a tool which is very important for algebraic geometry when we're considering certain algebraic varieties as groups, because then we can reduce a lot of our problems about the question of an entire category to the question about a group. It's the same idea that I have presented beforehand when we were talking about our example with GL2, when we started with the entire functor and then we ended up with our Hopf algebra. Exactly. So this is the entire idea. Unfortunately, I didn't have the time to go into some examples, so I'm very willing to show some examples during the apéro. Afterwards, I'm done with my talk, and yeah, I'm very happy for attendance.